Optoelectronic Integrated Circuits, or OEICs, resolve data bottlenecks by merging optical communications and silicon logic on a single semiconductor substrate. Modern electronic microprocessors achieve high density because they rely on metal interconnects. These metallic traces scale down to sub-10 nanometer dimensions, allowing engineers to pack billions of logic gates into a confined physical space. But optical components require dielectric waveguides to carry photons. These structures are restricted by the diffraction limit of light. A photon cannot be contained within a 5 nanometer trace. This spatial mismatch forces a micron-scale optical waveguide to sit directly alongside a nanoscale electronic wire. Beyond the spatial mismatch, there is a material barrier. Standard electronic logic is built on silicon. However, silicon possesses an indirect bandgap, meaning when electrons are excited, they release energy as heat rather than light. It cannot emit light efficiently. Because we cannot shrink the light and we cannot make standard silicon glow, engineering an OEIC requires a radical physical compromise. We must integrate light-generating materials directly with silicon logic. To build complete optical transmitters and receivers, engineers must integrate 3,3 compound semiconductors, which emit light, and thin-film lithium niobate, which modulates it, onto standard silicon substrates. This integration architecture matrix shows 3 approaches to solve this material mismatch: hybrid, monolithic, and heterogeneous integration. Choosing between them requires balancing specific physical trade-offs: electrical parasitic losses, chemical lattice mismatches during growth, and mechanical alignment tolerances during assembly. Evaluating the physics of these 3 paths reveals the hardware requirements for next-generation hyperscale data centers. In a hybrid integration model, optical and electronic devices are fabricated separately on their native substrates. They are then packaged together on a shared carrier using physical connections like microsolder bumps or wire bonds. Hybrid integration is optimized for material quality because every device is grown according to its specific chemistry. The flaw in this method lies in the physical wires connecting the separate chips. These discrete connections introduce electrical parasitics. Consider the physics inside an optical receiver. The photodiode has inherent parasitic capacitance, labeled here as CP. When you connect that photodiode to a transimpedance amplifier across a wire bond, you introduce additional capacitance and inductance. Together, these create a dominant low-frequency pole at the input node. Because of this parasitic pole, the signal rolls off prematurely. The physical distance the electrons must travel across the wire bond places a ceiling on the maximum frequency the receiver can process. To bypass this physical limitation, engineers design complex shunt feedback amplifiers or regulated cascode input stages. These use active local feedback loops to lower the input resistance and isolate the capacitance. Monolithic integration requires all active and passive components to be fabricated on a single continuous semiconductor substrate to eliminate packaging parasitics. By keeping everything on chip, monolithic designs eliminate packaging overhead, providing a path toward terabit scale data rates. The obstacle to monolithic integration is the chemistry. Direct heteroepicaxy, growing 3 IV materials directly on top of silicon, faces a severe lattice mismatch of roughly 4%. To grow these materials, the wafer is heated to over 800 degrees Celsius. Cooling the wafer to room temperature causes tensile stress, tearing the crystal structure and spawning threading dislocations that propagate vertically through the active layers. These physical defects act as non-radiation recombination centers. If a photon or an electron-hole pair encounters one of these dislocations, the energy is absorbed and neutralized, destroying the material's optical gain. To address this, engineers insert dislocation filter layers, alternating strained superlattices between the silicon and the active region. The strain in these layers forces the vertical dislocations to bend sideways and annihilate one another. While filter layers reduce the defect density, they do not eliminate it. The remaining defects are managed through the use of self-assembled indium arsenide and gallium arsenide quantum dot lasers. Unlike a continuous quantum well, quantum dots confine charge carriers in 3-dimensional nanoscale volumes. If a threading dislocation propagates through this active region, it only deactivates the specific dots it directly intersects. The surrounding dots remain isolated and functional. Because quantum dots provide this spatial defect tolerance, they make monolithic integration viable on silicon substrates. Heterogeneous integration involves transferring thin-film semiconductor layers or pre-processed microdevices from their native substrates to a target host wafer. This approach matches the material quality of hybrid integration with the low parasitic profile of monolithic architectures. Deterministic microtransfer printing, or MUTP, is the primary assembly method enabling this hybrid approach. This process uses an engineered elastomeric PDMS stamp. By controlling the speed of the stamp, engineers exploit rate-dependent adhesion to pick up arrays of microscopic active devices from their source wafer and print them onto a silicon host with sub-micron precision. This method minimizes the waste of expensive 3IV compounds, placing them only where optical gain is needed, while utilizing the silicon host wafer for passive optical routing. This is applied to the 2 to 3 micrometer mid-infrared spectral range, which is critical for sensing environmental gases and biomedical markers. Engineers are transferring gallium antimonide active gain chips directly onto silicon-on-insulator host platforms. The successful 3D integration of these gallium antimonide gain chips using microtransfer printing demonstrates the industrial maturity of this manufacturing method. Heterogeneous integration achieves the low interconnect parasitics of monolithic systems, bypasses lattice matching penalties, and provides a scalable solution for mass production. The architectural goal driving these integration methods is the transition from pluggable transceivers to co-packaged optics. In a CPO architecture, high-density optical engines are relocated from the board's edge directly onto a shared package substrate with a high-power ASIC. This keeps the electrical traces short to prevent signal degradation, but placing signally sensitive optical components next to a compute die creates significant thermal crosstalk. High-speed ASICs generate immense heat. As this washes over the optical engines, it shifts emission wavelengths, misaligning multiplexing channels. To mitigate this, engineers physically remove the light sources, placing them in an isolated external laser source module. Managing this thermal environment now dictates the physical layout and architecture of modern co-packaged optics. The demands of co-packaged optics prove no single material can solve every problem on the chip. The future of OEICs is inherently a multi-material platform. For passive routing, silicon nitride provides low-loss waveguides and high tolerance to optical power. For converting electrical signals to light at high speeds, thin-film lithium niobate offers electro-optic modulation bandwidths over 100 GHz at low driving voltages. For light generation and amplification, monolithic 3V quantum dots provide temperature-stable on-chip lasers. Next-generation optoelectronic integration relies on the heterogeneous assembly of optimized physical materials to process data at the speed of light.